For Lesson 2.5, Energy and Power in Electric Circuits. Let's now look at some energy and power relationships in electric circuits. As charge passes through the circuit element, the electric field does work on the charge. In a source of EMF, additional work is done. If the potential at A is lower than at B, then VAB is negative. Okay? And there is a net transfer of energy out of the circuit element. The element then acts as a source, delivering electrical energy into the circuit to which it is attached. This is the usual situation for a battery, which converts chemical energy into electrical energy and delivers it to the external circuit. Thus, QVAB can denote either a quantity of energy delivered to a circuit element or a quantity of energy extracted from that element. In electric circuits, we are most often interested in the rate at which energy is either delivered or extracted from a circuit element. And the time of energy transfer is equal to power, and denoted by P. So we write power is equal to VAB times the current. So the unit of VAB is 1 volt or 1 joule per coulomb, and the unit of I is 1 ampere or 1 coulomb per seconds. Hence, the unit of power is equal to 1 watt as it should be. So, for a voltage VAB, 1 joule per coulomb, and the current C over coulomb over seconds. So, makancel si coulomb. Ang matitira is si joule per second, and 1 joule per second is equivalent to 1 watt. This is why power is 1 watt. Electrical power delivered to the resistor by the circuit is P is equals to VABI is equals to IR is equals to VAB squared over R. Kung paano na yan nangyari, will not explain that thoroughly, but just remember this equation 2.15. It is a relationship between 1 to 3 relationship in 1. So power, again, is equals to voltage AB times the current is equals to I squared R is equals to VAB squared R. Bakit siya tatlo? It's either sa problem given ang current lang, or given si R, or given si VAB. It's either of the 3 variables that are given in a problem, makukompute natin si power. Current enters the higher potential terminal of the device. Represents the rate of transfer of electric potential energy into the circuit element. What becomes of this energy? The moving charges collide with atoms in the resistor and transfer some of their energy to these atoms, increasing the internal energy of the material. Either the temperature of the resistor increases, or this is a flow of heat out of it, or both. So, another form of transferring a resistance or the moving charges collide with atoms is heat. Okay? Either the temperature of the resistor increases, or there's a flow of heat out of it, or both. In any of these cases, we say that energy is dissipated in the resistor at a rate I squared times R. Every resistor has a power rating. The maximum power the device can dissipate without becoming overheated and damaged. This is why there's a small wire and there's a big wires that has different power rating. Kung napansin nyo sa isang wire, makikita nyo na may mga printed yan siya, dyan, and dyan yung mababasa kung ano yung power rating nila. Some devices such as an electric heaters are designed to get hot and transfer heat to their surroundings. But if the power rating exceeded, even such a device may melt or even explode. Power output of a source. In figure 2.7, a car battery is connected to one of the car's headlights. Point A is a higher potential than point B. So VA is greater than VB, and VAB is positive. Note that the current I is leaving the source at the higher potential terminal rather than entering in there. Energy is being delivered to the external circuit at a given equation 2.14. This one. For a source that can be described by an EMF and internal resistance R, we find that power is equal to VABI or equal to EMF times I minus I squared times R. Just remember this equation and I will not dig into this why or bakit siya naging ganyan. The term I squared R is the rate at which electrical energy is dissipated in the internal resistance of the source, and the difference EMF I minus I squared R is the net electrical potential output of the source. So this is the real electric power of a source. That is the rate at which the source delivers electrical energy to the remainder of the circuit. Power input into a source. An automobile battery in figure 2.8 being charged by the car's alternator shows a practical example of when two sources are connected in a simple loop circuit. The source with the larger EMF delivers energy to the other source. Because of this reversal of current I, instead of equation 2.12, we have the upper source, equation 2.17. Power is equal to VAB. Now it becomes positive. When we are power input, remember that, power input, magiging positive. Sa power output, it's negative. Work is being done on rather by the agent that causes the non-electrostatic force in the upper source. There is a conversion of electrical energy into non-electrical energy in the upper source at a rate EMF times I. And the term I squared R in equation 2.17 is again the rate of dissipation of energy in the internal resistance of the upper source. And the sum EI plus I squared R is the total electrical power input into the upper source. This is what happens when a rechargeable battery is connected to a charger. The charger supplies electrical energy to the battery. Part of it is converted to chemical energy, to be reconverted later, and the remainder is dissipated or wasted in the battery's internal resistance, warming the battery and causing a heat flow out of it. If you have a power tool or laptop computer with a rechargeable battery, you may have noticed that it gets warm while it is charging. So power input to a source is a combination of EI plus I squared R. But when we are using the power output or the battery, it becomes I. Of course, ginagamit mo na siya. When we are using, minus. When we are storing, positive. Or charging, positive. Now, learning activity 2.7. Power input and output in a complete circuit. For a circuit that we have analyzed in learning activity 2.5, we find the rates of energy conversion, chemical to electrical, and energy dissipation in the battery. The rate of energy dissipation in the 4 ohm resistor and the battery's net power output. So from the previous problem, this is a similar figure, and in a layman's term, ganito siya. Now, the sketch above shows the circuit, gives values of quantities known from example 2.5, and indicates how we find the target variables. We use equation 2.16 to find the battery's net power output. Okay? The rate of chemical to electrical energy conversion, and the rate of energy dissipation in the battery's internal resistance. We use equation 2.14 to find the power delivered to and dissipated, the 4 ohm resistor. So, from the first term in equation 2.16, the rate of energy conversion in the battery is EI. So, 12 volt times 2 ampere is equals to 24 watts. Saan nanggaling yan? This is given from the figure or from the problem itself. So, from this problem, current is equals to 2 ampere and the EMF is equals to 12 volt. So, the rate of conversion in the battery is 24 watts. From the second term in equation 2.16, the rate of dissipation of energy in the battery is I squared times R. I is 2 ampere, that is squared. 2 squared is 4, and the internal resistance R is 2. So, 4 times 2 is 8 watts, and the net electrical power output of the battery is the difference. 24 minus 8, output kasi siya. So, 24 minus 8 is equals to 16 watts. And the electrical power output or the power input is equal to the rate of dissipation of electrical energy in the 4 ohm resistor. And that's 16 watts. Now, increasing the resistance. Suppose we replace the external 4 ohm resistor in the above sketch with an 8 ohm resistor. How does this affect the electrical power dissipate in this resistor? Simply replace the 4 ohm by 8 ohm. So according to 2.15, the power dissipated in the resistor I squared R, you might conclude that making the resistance R twice as great as in example 2.6 should also make the power twice as great. If instead you use the formula P, VAB squared over R, you might conclude that the power should be 1/2 as great as in the preceding example, 12 or 16 watts over 2 is equals to 8 watt, which is correct. In fact, both of these are incorrect. Okay? The first is wrong because charging the resistance R also charges the current in the circuit. And remember that a source of EMF does not generate the same current in all situations. And the second answer is wrong because the potential difference VAV across the resistor changes when the current changes. To get the correct answer, we first find the current as we did in example 2.5. What is the current? Now, replacing the 4 ohm into 8 ohm, we have 1.2 ampere. So the current is 1.2 ampere. The greater resistance causes the current to decrease. Remember that. The greater the resistance causes the current to decrease. So naglaki siya, meaning lumiit si current. Now, the potential difference across the resistor is VAB is equal to IR to 1.2 times 8 is just equals to 9.6 volts, which is greater than that with the 4 ohm resistor. We can then find that the power dissipated in the resistor in either of two ways, okay? Ginamit yung two-way to solve the power is when we are given the I and the R, or the VAB and R. So I squared 1.2 squared times the 8 is equals to 12 watts is also the same sa 9.6 squared over 8 equals 12 watts. As an evaluation, increasing the resistance R causes a reduction in the power input. Remember that. To the resistor. In the expression P is equals to I squared R, the decrease in current is more important than the increase in resistance. In the expression P VAB squared R, the increase in resistance is more important than the increase in VAB. Remember this. This same principle applies to ordinary light bulbs. A 500 watt light bulb has a greater resistance than does a 100 watt light bulb. Learning activity 2.9, power in a short circuit. For the short circuit situation of learning activity from the previous, find the rates of energy conversion and energy dissipation in the battery and the net power output of the battery. Our target variables are again the power inputs and outputs associated with the battery, and the sketch above shows the circuit. This is the same situation. I'm sorry. This is the same situation as in example 2.6, and we found that in example 2.6 the current in the situation I is equal to 6 ampere, and from equation 2.16 the rate of energy conversion, the EMF times I, is equals to 72 watts. At the rate of dissipation of energy in the battery is I squared R, also 72 watts. And the net power output of the source is EI times I squared R equals to 0. We get the same result from the expression P VABI because the terminal voltage VAB of the source is 0. Okay. Now, with ideal wires and ideal ammeter, R is equal to 0, all of the converted energy from the source is dissipated within the source. This is why a short-circuited battery is quickly ruined and may explode.